This video will present data from the launch of the Mars 2020 mission, which can be analyzed to understand how Newton's second law of motion describes the mathematical relationships that exist between force, mass, and acceleration. The Mars 2020 mission launch vehicle was an Atlas V541 rocket supplied by United Launch Alliance. The launch took place on July 30th, 2020, beginning a 7-month voyage that will bring the Perseverance rover and Ingenuity helicopter to Mars. The goal of this video is to provide a summary of the main events that took place during the launch. Before launch, the Atlas V rocket is demonstrating Newton's first law of motion, which states that an object at rest will stay at rest unless acted upon by an outside force. The forces acting on the rocket before launch are the gravitational force and the normal force. The weight of the rocket, Fw, is caused by gravity pulling down on the mass of the launch vehicle. The mass of the fully fueled rocket was 531,000 kilograms. The other force acting on the rocket is the normal force, Fn, which is the Earth pushing up on the rocket. The two forces are balanced, so the inertial reference frame does not change, which is science for look at the rocket not moving. After the boosters are ignited, a third force begins to act on the rocket. The thrust force is an example of Newton's third law and is caused by the propulsion of the exhaust of the rocket engines. As the working mass of the exhaust is propelled down, a reaction force pushes the launch vehicle up. Once the thrust-to-weight ratio is greater than 1, the rocket will begin moving upward and will continue to accelerate because the force of the thrust pushing the Atlas V up is greater than the force of the gravity pulling down on the rocket. As the rocket gains velocity, an additional force will act on the rocket. The resistive drag force is caused by the movement of the rocket through air. The initial thrust is provided by 4 solid rocket boosters, SRBs, and the Atlas V Common Core Booster, CCB. The SRBs provide 1,688.4 kilonewtons of thrust force and have a burn time of 94 seconds, and were jettisoned at about 1 minute and 50 seconds after launch.
And we have a good indication of SRB jettison of all 4 SRBs, and the vehicle has gone to closed-loop guidance.
The payload fairings were jettisoned about 3.5 minutes into the flight.
And we have good indication of payload fairing jettison and Centaur forward load reactor deck jettison.
The Atlas Common Core Booster provides a maximum thrust force of 3,827 kilonewtons at sea level and up to 4,152 kilonewtons in the vacuum of space. The CCB burned until about 4 minutes 20 seconds after launch. The booster stage separated from the Centaur stage just before the 4.5 minute mark of the flight.
ECO booster engine cutoff, standing by for stage separation. And we have good indication of Atlas Centaur separation.
So there you're seeing live footage.
And we have
the
Mach
rocket.
1, RL-10 operating.
The upcoming footage includes the flight data from 26 seconds until 290 seconds after launch.
Coming up on 30 seconds into flight, the RD-180 is throttling down as expected. Engine response looks good. And Mach 1, Atlas V is now supersonic. And passing 45 seconds into flight, vehicle is now passing through max Q, maximum dynamic pressure. And passing 1 minute into flight, the RD-180 is throttling back up as expected. Engine response looks good. At this time in flight, the SRB chamber pressures remain nominal. The RD-180 pump speed and fuel injector pressures are responding well to demands on the engine. Standing by for SRB burnout shortly. And we have burnout on all 4 SRBs. Burnout pressure signatures look good. Standing by for SRB jettison shortly. And we have a good indication of SRB jettison of all 4 SRBs. And the vehicle has gone to closed loop guidance. Vehicle body rates are responding nominally at this time. And coming up on 2.5 minutes into flight, the RD-180 is throttled down slightly as expected. Engine response continues to look good. At this time, the vehicle is 50 miles in altitude, 85 miles downrange, traveling at 6,000 miles per hour. And the Centaur reaction control system is now pressurizing to flight levels. And just past 3 minutes into flight, the RD-180 is now throttling to maintain a constant 2.5 G acceleration limit for payload fairing jettison. Engine response and vehicle acceleration look good. And we have good indication of payload fairing jettison and Centaur forward load reactor deck jettison. And the RD-180 is throttling back up to attain a 4.6 G acceleration. Engine response continues to look good. And Centaur has begun the boost phase chill down sequence to thermally condition the RL-10 for operation. Standing by for BECO shortly.
BECO's the call for booster engine.
And we have BECO, booster engine cutoff, standing by for stage separation. And we have good indication of Atlas Centaur separation.
So that you're seeing live footage.
And we have
the
Mach
rocket.
1. RL-10 operating parameters look good. Chamber pressures are stable.
Velocities in the NASA footage are reported in miles per hour, mph. This will need to be converted to meters per second for the analysis. At 26 seconds, the velocity of the rocket was 1,204 miles per hour. This can be converted to meters per second by multiplying by a series of conversion factors. 1 mile equals 1.609 kilometers, 1 kilometer equals 1,000 meters, 1 hour is 60 minutes, and 1 minute is 60 seconds. So the velocity of the rocket 26 seconds after launch was 538.1 meters per second. Another way to perform the conversions of the velocities is to use the Google Unit Converter. This Google tool uses the exact relationship of 1 mile being equal to 1.60934 kilometers. So the online tool may produce converted values that are slightly different than calculations performed using the rounded conversion factor. When recording data for the analysis, all time should be reported in units of seconds. For example, 1 minute 10 seconds should be reported as 70 seconds. I've added text giving the time converted to seconds in this video. After the launch footage ends, I'll share a breakdown of the masses of the separate components of the rocket and the rocket fuel. This table summarizes the masses of the different components of the Atlas V541 rocket, along with fuel masses. Some masses are estimates based on published data from United Launch Alliance and NASA. The payload, which includes Perseverance, Ingenuity, and the landing system, was 8,290 kilograms. The payload fairing was 4,649 kilograms. The Centaur stage had a mass of 2,316 kilograms with a fuel mass of 20,830 kilograms for a total of 23,146 kilograms. Each SRB, solid rocket booster, had a mass of 4,067 kilograms with 42,630 kilograms of fuel for a total mass of 46,697 kilograms. The Perseverance launch vehicle had 4 SRBs, each with a burn time of 94 seconds and a maximum thrust of 1,688.4 kilonewtons. The Centaur interstage adapter had a mass of 1,266 kilograms, and the Common Core booster interstage adapter had a mass of 278 kilograms. The Common Core booster had a mass of 21,173 kilograms and a fuel mass of 284,089 kilograms. The burn time for an Atlas V CCB is 253 seconds. The maximum thrust the CCB can supply at full throttle is 3,827 kilonewtons at sea level and 4,152 kilonewtons in the vacuum of space. NASA reported the weight of the launch vehicle before ignition was 531,000 kilograms, which means that there was an additional mass of approximately 1,400 kilograms. The rocket parts that made up this additional mass include the Centaur forward load reactor, the Centaur aft stub adapter, the 5-meter payload fairing boat tail adapter, and the CCB cylindrical interstage adapter. To perform a graphical analysis of the data presented in this video, there are a few key things to keep in mind. A graph plotting velocity, measured in meters per second, versus time, measured in seconds, can be used to find the acceleration of the rocket in units of meters per second squared. The acceleration can be determined by performing linear regression analysis of the data and finding the slope of the line. The acceleration of the launch vehicle changed throughout the mission at several key points. So some options for running the analysis include finding the average acceleration, the maximum acceleration, the minimum, and acceleration at key points of the mission. I will post a video in the future to provide some examples of how to use Google Sheets or Microsoft Excel to perform this analysis. Thank you for watching. I hope you found this video helpful. Please keep checking back to my channel for new videos about Perseverance and the Mars 2020 mission.